So in the previous class, when TA talked about the homework problems, you guys raised a question, and she told me that you had a question about how to calculate the main effect for dispersion, right? Dispersion. So here we have two response variables. So those are our factors. Right here. So those are the factors. So factor has effect, okay, may impact our response variables. This is a mean. This is a dispersion. Okay? The way we calculate the effect on the response y bar is actually we take this column and this column and then multiply them together, then sum them up, divided by 8. So if you want to do the interaction or 3-way interaction, 4-way interaction, you just follow the same practice. For dispersion, you do the same. You just use this column multiplied by dispersion. And then you do the divided by half of the size of the runs. So here, those are the effect. You see, this is the effect. Factor A's effect, main effect, on my response y bar. And factor A's effect on my dispersion. Okay, makes sense? And the same way we can do it for 2-way interaction, 3-way interaction, and 4-way interaction. So this is just one quick review of quick answer to the question you have about how to calculate the main effect on the dispersion. So now let's get back to the statistic process control charts. So this one is control charts for variables. Okay, variables, if you are monitoring something in the production process, okay? So for example, if you have a temperature controlled room, you take the temperature recordings in every maybe second, then you see how the fluctuation of the temperature, okay? How can you tell this room is well controlled or not? So if somebody asking you how to please monitor this process, tell me when the process is out of control. Then what kind of characteristics are you going to monitor in the curve? The first one, so what are you going to look for in the data? If you are monitoring critical characteristics of different samples. So we are looking at the deviation. The first one, whether there is the variable is a quality characteristics that can be measured on a numeric scale, so continuous variables. So we have central tendency and dispersion. So if we assume this is a normally distributed, okay, then every time we just randomly take samples out of this distribution, or randomly take random numbers, we should monitor the process mean and process variability. We want to see whether every time we take a sample, whether it is drawn from this distribution, or we have a mean shift from mu0 to mu1, or from sigma 0 to sigma 1. You see, this is a dispersion. This is a variability. This is a mean shift. Okay. How to monitor the mean shift? That is called X-bar chart. How to monitor the variability of the process? We can use R chart or S chart. So we have process mean, mu0, variance, sigma 0 square, standard deviation will be sigma 0. The mean shift, mu1 could be shifted to be smaller, or mu1 could be bigger. So this is called a mean shift. This is a typical pattern you are going to look for when you are monitoring a process. So the other one is the process variability. Process variability means originally you have a small variation, but suddenly you have a large variation. Okay, you want to see what's going on over there. Okay, so this is a process variability getting bigger. So if your process variability is getting smaller, is it good or bad? Ian, good or bad? Process variability getting smaller.
It's good.
Yeah, it's good because process variability getting smaller means quality is higher, right? Very good. Good job. So statistic basis of control charts. So at each time point, for example, T1, we collect a sample. So when we collect a sample means it's a sample of size n. Within this sample, I have multiple observations. Okay, this is like a batch. Okay, so this is multiple observations I have, x1 to xn. Then I have x1 bar and R1. What is R1? Anybody? What is R1? What does R stand for? The range. R stands for the range. R1 stands for the range of this first sample. And then I have R2, R3, and to Rm. Okay? Now, this is x1 bar. But now what I have x bar. I have 2 bars. What does this 2 bar mean? Anybody? Grand average. You take this is the average of the first sample, this is the average of the second sample. But if you take average of everything, that is called a grand average. Okay? So x bar means you have mean for each sample, like x1 bar, x2 bar. And then you have the mean of all the samples. Okay? So this is called a grand average. And the R bar means you are going to take the range for the sample 1, range for sample 2, you're going to average them together. So you're going to have x bar, x bar, R bar, and R1 is the maximum minus the minimum in the first sample. Then, you know here, for the first sample, we're taking the average. If we are going to take the average, we have the central limit theorem. Okay? If x1, x2, xn is a samples of size n, now we get x bar. This is a distribution of x bar. So this is central limit theorem. X is normally distributed with mu sigma square. X bar will be normally distributed with mu and sigma square over n. Okay? Over n. The variability is getting smaller because you are taking the average. Make sense? Okay? So now this is a population mean of x bar and the population standard deviation of x bar. So what is the probability that sample mean will fall into this range? We know this is what we did before. This is confidence interval. So this is 1 minus alpha, 100%. Okay? So central limit, control limit for x bar chart. So we are actually using the x bar plus A2 R bar. So this is the center line. So in the control charts, we have 3 critical lines: center line, upper control limit, and lower control limit. And how do we get this estimation of the sigma hat? Okay? The sigma hat is actually R bar divided by D2. But how do we get D2? So D2 is available in this over here. You see here, this is all the, because when in each sample, when the sample size is different, we are using different A2, A3, or just now we were talking about D2, right? So this is the factors for center line. Okay, factors for center line. Now we are using the range control chart, so we are using D2. So we use sigma hat estimation divided by D2. And based on different sample size, we are going to find different D2 values. If we are going to look at this, okay, so there are several technical terms in control charts. The first one is upper control limit and lower control limit. Center line, sample size, and then we have process capability ratio. I'm going to talk about this, and the process standard deviation. So x bar is the average of measurements. X bar is the average of averages. And this is a range. R bar is the average of ranges. And then we have upper specification limit and a lower specification limit. Now first, let's have a look at the variable data. the control chart. This is X bar and R control charts. You see here, what we need to find out is the upper control limit is X bar plus A2 R bar, and then we have center line is X bar grand average. But how to get this A2? A2 varies with the sample size, and depending on the sample size you have, you're taking different A2, and then you plug in this equation because you know R bar, you know X bar, so you will be able to plot this control chart, and based on the control chart you're going to see whether your points get out of this control chart or not. What happened? Computer just shifts by itself. And also we have R control chart. R control chart, you're monitoring the range to see the range, what is the variation of the range. Then you have D3 and D4. So D3 and D4, they are also varying with respect to the sample size. You are taking different D3 and D4. So here, capability study. Capability is the upper specification limit minus the lower specification limit divided by 6 sigma hat. So sigma hat is the estimation of the process standard deviation. So sigma hat equals to R bar divided by D2, and D2 is right over here, and based on different sample size, and you estimate the sigma hat in different ways. Okay? Now let's get back to this one, and so now we have the upper control limit and center line and lower control limit, and we know how to calculate A2. Okay, A2 right here, A2, and D2. D2 see the table for the D2 values. So in this way we will be able to get the X bar chart. And similarly, how to do for R chart? R chart we need D3 and D4. So you have R1, R2, and 2RM. You want to see whether this R and is inside the control limit or not. If it is outside the control limit, which is called out of control. Then everything is based on the 3 sigma control chart. We have R bar plus 3. And this is the estimation of the standard deviation of my R, and basically this is the estimation of my standard deviation of R, because the estimation, this is a process standard deviation estimation. Process standard deviation estimation is actually R bar divided by D2, and sigma R, this is a standard deviation for the range. This is a standard deviation for the process. So this is a D3 sigma hat. Okay. Okay, as we discussed just now, we have a new term called process capability ratio. Process capability ratio, also called CP. So for process with both upper and lower specification limits, CP equals to upper specification limit minus the lower specification limit divided by 6 sigma. Okay, 6 sigma is is minus 3 sigma to the plus 3 sigma, and the CP is the higher the better. Why higher the better? It's right here. Why higher the better? Okay. Now, for this one, you see this is a specification limit. Specification limit is what the customer wants. Okay? And this is a control limit. This is what you can deliver. So customer wants this big, this range, but you can deliver in a very small, high precision range. Okay? You can deliver in this range, but the customer wants this. That means you are doing better. Okay? If CP is higher, CP greater than 1, that means you are doing very well. and CP equals to 1, your process capability is just about the same as what the customer wants. And CP less than 1, that means you are not doing that well. Customer wants this range, but you can deliver only in a very bigger range. That means you are not doing very well right here. So when CP less than 1, a large number of non-conforming items are produced. When CP equals to 1, about 0.27% of non-conforming are produced. CP greater than 1, a very low number of non-conforming items are produced. Okay? So this is CP, and 1 over CP 100% is a percentage of the specification band used by the process. Now, people always talk about phase 1 control chart or phase 2 control chart. What does it mean? So phase 1 control chart is a trial control limits. So M initial samples, and then we are going to build the X bar chart and R chart. This is highly desirable if we have 20 to 25 samples of size N. Typically, each sample, the size, is between 3 and 5. So if all points plot inside the control limit and no systematic patterns, the process is in control, was in control in the past. And then the trial control limits are suitable for controlling current and future productions. So now, this is in control, inside the control limit. If the points plot outside the control limit, we call it out of control. So we revise the trial control limits. Then we examine the out of control points, look for assignable costs. And then we find the cost, we will eliminate the root cause and then discard this point, recalculate the control limit. If we didn't find the root cause, then we discard the point, no analytical justifications. Or we retain the points, considering the trial control limits as appropriate for current control. Okay? And this is the famous, we call it Pdca. In IE, we have Pdca. Okay? What is Pdca? Pdca means first you plan. Okay? You plan first, and then it's actually this figure is better. But this one is so small. Let me just use this one right here. Pdca means you plan your production, and then do the control limit, phase 1, and then you perform, okay, as you are doing the production, and then you check whether they are out of control. If they is out of control, you improve the process, and then you do it again. So this is called Pdca cycle. Plan, do, act, plan, do, check, and act. And this is exactly what we are doing right now over here. Phase 1 is trying to establish the control limit. This is called trial limit. You are based on the historic data. You are just doing a lot of experiments and try to establish the control limits. But phase 2 is the operation of the X bar and R chart. That means in phase 2, you have already established the reliable control limits. Now we are going to use it monitor future productions. Okay? So the control limits are functions of the natural variability of the process. And there's another term called natural tolerance limit. Okay? Lateral tolerance limit is the upper lateral tolerance limit, lower lateral tolerance limit. It's 3 sigma above and below the process mean. Okay. And the specification limit, we have already talked about this. This is determined by the management, manufacturing engineers, customers, and the product developers or designers. No mathematical relationship between control limits and the specification limits. Okay. Now, again, we talk about 2 charts, X bar chart, which is used to monitor the between sample variability. R chart is monitor the within sample variability. This is a mean to next mean to the next sample mean. You see how does it vary. However, R chart is monitoring within a sample. You have range, and you want to see this range, how does it vary over time. So this is monitors the within sample variability. X bar chart monitors the between sample variability. So guideline for the design of control chart. First, we need to decide, okay, what will be the sample size. If you're going to take a sample, how many observations are you going to connect inside this sample? Second, control limit, and then frequency of sampling. How frequent you are going to take the sample. So these are some general guidelines. So for X bar chart, moderate to large process shift, we use small sample size. Okay? If you have a moderate to large process shift, so n equals to 4, 5, 6 may be okay. But if you have very small process shift you want to detect, then you need a large sample size. Usually the large sample size we mean 15 to 25. So if increasing the sample size is not an option, because sometimes it's very difficult to increase the sample size. Then we use sensitizing rules, that is warning limit. So previously we have plus minus 3 sigma. Now warning limit is plus minus 2 sigma. So R chart is relatively insensitive to standard deviation shift for large sample size. It will be better to use S chart instead of the R chart. Okay, I'm going to talk about S chart in the next page. So allocating sampling effort. So based on the resource or cost we can afford. So large sample, less frequently. Small sample, more frequently. So this is industry practice. Most of the time, industry practice favors small sample and more frequent observation. Now, we discussed the control chart for X bar and R chart. Now let's have a look at the X bar and S chart. So by its name, R chart, we're monitoring the range. S chart, we're going to monitor the standard deviation. Okay, sample standard deviation. So this is preferable when sample size n is moderately large and greater than 10 or 12. Sample size is variable. Okay. So this is how to calculate the sample variance. This is the estimator of the population variance. Okay. So S squared is the unbiased estimator of the population variance. However, S is not an unbiased estimator of sigma. Okay, S is actually, in order to estimate this S, we are actually using C4, sigma. C4 depending on the sample size. And the standard deviation of S is actually sigma square root 1 minus C4. Okay? So every time we take a sample, we have X1 bar, S1, X2 bar, S2, Xm bar, and then Sm, based on the sample data we have. We calculate the sample mean and the sample standard deviation. Now our goal is to monitor this sample mean and sample standard deviation over time. Okay, so this is S bar. So S bar over C4 will be an estimation of the sigma hat. But how to get C4? So for S chart, if we want to get C4, it's right over here. You see, this is a chart for ranges. Then you have center line, and you have control limits, D3, D3, D4. And this is what we need for X bar chart and also R chart. And here is the C4. You see C4? This is for the S chart. Okay? And this is for the X bar chart. So here, we have X bar chart and also S chart and R chart, all the constant values we have. So over here we have C4, obviously depending on the C4. What the C4 is for a particular sample size. Now if we have a sample size 10, then C4 will be 0.9727. And 1 over C4 will be 1.0281. Now 3 sigma control limit for S. So this C4 sigma, okay, and this is S bar. S bar is actually equals to C4 sigma. And here it will be C4 sigma plus 3 sigma 1 minus, because this is average plus minus 3 standard deviation. But for S, the standard deviation is this. So this sigma 1 minus C4 square is the standard deviation for my S. Okay. So up to now, we will be able to get the upper control limit, center line, and lower control limit for the S chart. So here is an X bar chart based on S. So X bar chart, you have X bar plus 3 sigma hat, but sigma hat is actually equals to S bar over C4. So you just replace this sigma hat with S bar over C4. Then you will be able to get A3. So this is X bar chart based on S. Okay. Now let me let's review all the formulas we have. So this is a formula for control charts. If we know the standard deviation, if we know the population mean and standard deviation, then X bar chart is very straightforward, because this is a mean plus minus 3 sigma. But here we are not using 3 sigma, Andrew. Here we are using 3 sigma over square root of n. Why? Instead of just mu plus minus 3 sigma. Because this is a standard deviation for the X bar. For every sample, you are trying to calculate a sample mean, right? So sample size is n, based on the central limit theorem. This is a standard deviation for X bar. We are not monitoring X, we are monitoring X bar. So that's why this is mu plus minus 3 sigma over square root of n. Okay? And for R chart, this is R, okay, plus minus 3 variation of the standard deviation of R. So then what we have here is, because we know the variation, so this sigma R will equals to D3 sigma, because we have already know the sigma. So we will be able to get the R chart. We will also be able to get an S chart based on the mu and sigma when mu and sigma are given. But in the real world industry practice, these two are not going to be given. So that's why we need to approximate this mu and sigma with the sample mean and sample variance. So formula for control chart, if they were not given, so unknown mu and sigma. So X bar chart using R, so this is X bar chart using R. Okay? And we are doing the X bar plus A2 R bar and minus A2 R bar. This A2 is actually equals to 3 over D2 square root of n. And this A2 value is actually available in the table that we were given. And also the R chart, you need R bar, and also you need a D4 R bar, D3 R bar. And this is also given in the table. And D3, D4, A2, they are not constant. They are actually varying depending on the sample size you have. So this D4 and D3. Now this is X bar chart using S. Okay, X bar chart using S. S is actually C4 sigma, and sigma S is sigma square root 1 minus C4 square. So based on this approximation, we get the upper control limit is X bar plus A3 S bar, and X bar minus A3 S bar. And then we also have the S chart. Then we need to use B3 and B4. So in summary, if we want to establish the X bar chart, we need A3, we need B4 and B3. Then we will be able to establish this control chart. Okay. So this is the end of the discussion of X bar chart using R and X bar chart using S. Now let's go back and I want to show you something. And how to use Excel to create the X bar chart. And I have a video lecture on how to use Excel to create a control chart. I believe if you got a quality engineering job in the future, you are going to do Excel and monitoring your process. And how are you going to do it? Let's download one of the Excel spreadsheet. Okay, so before we download, I want to show you this one. This is a video lectures. And I have video lectures for X bar R chart and then for the P chart. If you are interested in how to create with using Excel, and I'm also going to show you right here. Okay. Now, before we talk about how to build the control chart, let's first have a look at this control chart. This is X bar control chart. You see in X bar control chart, we have first we have this center line. Center line is the X bar right over here. And then we have this dot line. Dot line is this is upper 1 standard deviation line. This is a lower 1 standard deviation line. And then we have this blue dotted line. Blue dotted line is upper 2 standard deviation walling limit and a lower 2 standard deviation walling limit. Then we have upper control limit and a lower control limit. Then you will have variation here, right? Okay, so those are the basic components of a control chart. But how to do it? Let's have a look at this example. The thickness of a printed circuit board, okay, an important quality parameter. Data on board thickness in inches are given in the table for 25 samples. You see, you have 25 samples. Each sample you have 3 boards. In each sample you take 3 boards, and then you are going to measure the thickness. So this is thickness of the first board, second board, and the third board. This is the first sample. Now, how to get this range? Anybody? How to get the range? How to get this range? Andrew?
Upper minus lower?
Yes. Getting this range is the maximum of this group and minus the minimum of this group. So obviously the maximum is this guy minus the minimum is this guy. Then you got a 0, 1, 1. See? And then X bar. This is X bar of this one, the first sample. And then we got the first sample mean, first sample range, and second sample mean and second sample range. Now we're going to monitor this X bar. In order to get this X bar, I need to get the upper control limit. So first I need to get the center line. How to get the center line? So this center line will be the... Now the first one is the double bar. How do we get the double bar? This double bar is actually the average of this column. Global average. And this will be our center line. And this is R bar. R bar is the average of this range, this column. Now we need to, in order to get X bar chart for R, what we need is X bar chart for R. We need A2, we need D3 and D4. Okay, we need A2. Now how to get A2? A2 is 1.023. How did we get this value? This value is got from this table. We want to get A2, And we got 3. Each sample, I have sample size 3. So this is 1.023. So that's why here I have 1.023. Then I got D2, D3, because I need D3 and D4. Okay, I need D3 and D4 first. Okay, D3 and D4. D3 is 0, D4 is 2.574. How did we get that? So D3 and D4, this is for sample size 3, so I got 0 and 2.574. So 0, 2.754. Then obviously, using the equation, we will be able to get the upper control limit and the lower control limit. And this will be, you see, if I click on this center line equals to x double bar. And upper control limit equals to x double bar plus A2 R bar. And the lower control limit equals to x double bar minus A2 R bar. Okay, and then this is a 3 standard deviation. Now, if you want to get the 2 standard deviation, it's actually 2 over 3. This one is 3 standard deviation, so that's why you will use 2 over 3, the same thing. And this will be 1 over 3. Just multiply 1 over 3. So 1 standard deviation line. Okay? And then the same thing for the upper control limit. It's actually R bar times D4. Oops. Lower control limit will be D0 times R bar. And the center line will be R bar. Okay? Now, in this way, we will be able to generate we just plot the control limit we calculated. We will have the upper control limit for our control chart, lower control limit for our control chart. You have the center line in the middle. I didn't plot the center line. And here, this will be the X bar control chart. And I just plot all the values over here so that I can draw the dotted line. Okay? So this is the R limit. R limit was plotted below. Okay? So if you click on the data, you will be able to see this is this data we are plotting. Okay? X-axis will be sample number. Y-axis will be X bar. But if I click the upper control limit, you see I'm actually plotting this line. It's a constant. Lower control limit, this column. Okay? So this is how we do the X bar and R control chart. So for the X bar control chart, what I need is actually X double bar plus A2 R bar, X double bar minus A2. I need A2. A2 can be retrieved from the table, and D3 and D4. They can all be retrieved from the table. And if we want to do the X bar S control chart, you see what we need is this one. Okay? And also B3 and B4, and this is my center line. So what we need is actually upper control limit is A3, okay, S bar, and B4, this is for the S chart, this is for the X bar chart. What we need is actually the A3, B3, B4. Same for that. So this page is actually the summarization of what we discussed. Formulas for control chart. This is the X bar chart using R, the X bar chart using S. And how to get these constant values. They are available in this SPC table. This is also available in the back appendix of the textbook. This is actually what I taken from the textbook. Okay, now we finished the X bar chart and S chart. Now let's have a look at the control chart for attribute. You see here, for every control chart, we have several components. The first component is center line, and then I have upper and lower 1 standard deviation line, upper, lower 2 standard deviation line, and 2 standard deviation line we call them warning limits, and 3 standard deviation line we call them upper and lower control limit. Okay, so this is plus minus 1 standard deviation, plus minus 2 standard deviation, plus minus 3 standard deviation. But because we are monitoring x bar, we are monitoring the standard deviation of x bar instead of x. Okay. Now, center line positioned at estimated mean. This is upper and lower 1 standard deviation lines, positioned at 1 standard deviation above and below the mean. So warning limit, 2 standard deviation above and below the mean. Upper and lower control limits, they are standard deviation above and below the mean. Okay, making sense? Am I making sense? Any questions? Okay. Now, previously we were talking about X bar chart, R chart, or S chart. They were for variables, okay? For the samples. Now we have some other charts for attributes. So what is the first one is P chart. P chart is a fractional non-conforming. So fraction non-conforming is the ratio of the number of non-conforming items in a population, okay, to the total number of items in that population. So this is a fraction non-conforming. MP chart is a number of non-conforming. It's not a fraction anymore. It's a number. How many of them non-conforming? So you want to monitor the fraction in each sample. What is the fraction of non-conforming? But for this one, is you are monitoring how many of them are non-conforming. And also we have C chart. C chart, there are many instances where an item will contain non-conformities, but the item itself, it is not classified as non-conforming. Okay? It is often important to construct control charts for the total number of non-conformities or the average number of non-conformities for a given area of opportunities. So the inspection unit must be the same for each unit. So this is a defect, and U chart is a defects per unit. If we found C total non-conformities in a sample of n inspection units, then the average number of non-conformities per inspection is actually U equals to C over n. Okay? That is the average number of non-conformities. So fraction non-conforming is actually derived based on the binomial distribution. So binomial distribution is what we discussed in 322. So all trials are independent. Each outcome is either a success or failure. The probability of success on any trial is given as P. The probability of failure is 1 minus P. So the probability of success is a constant. So those are the 4 elements of a binomial distribution. Now, N will be the number of units of products selected at random. And D is the number of non-conforming units from the sample. P will be the probability of selecting a non-conforming unit from a sample. So you see here, probability number of non-conforming equals to X. Total you have N, right? So it's like select X out of N, then this is a probability X, they have defects, non-conforming. And then 1 minus P, N minus X, they are conforming. So for binomial distribution, the mean is NP, the variance is NP 1 minus P. Okay? And the sample fraction non-conforming is given as P hat equals to D over N. Okay? The fraction non-conforming is a random variable with mean P, okay, and the variance P 1 minus P divided by N. Now, this is a theoretical foundation for the P chart. Now, if we have n preliminary samples from the process, while the number of items, okay, n may vary from sample to sample, it is customary for each of the samples in a given application to include the same number of items. That means you have samples, okay? You have m samples. Now in each sample you have n items. This n is the same. Now di is the number of defective units in the sample. Then the fraction defective or the proportion defective will be di over ni. Because ni is the sample size and di is the number of defective in this sample. So this will be the fraction that is defective for this ith sample. Then we have the p bar. This is the estimate of the overall mean. So you have d1, the number of defectives in the sample 1, and then sample size, the sample 1 size, the size of sample 1, size of sample 2. Then this is the total defective, total items. So when all samples have n items, this will equals to p bar, p1, p2, plus pm divided by m. Okay? The estimated standard deviation of the process proportion defective will be SP, p bar 1 minus p bar over ni. This is a square root. Now based on what we have discussed, the p chart, first we got the total defective divided by total sample size. Then this is p bar. Then one standard deviation line, plus minus 1 standard deviation. Then plus minus 2 standard deviation. But we have a p. This is a standard deviation of my p. Okay, p is a proportion defective. And then plus minus 3 standard deviation. And this is the SP. Now let's have a look at this example, okay? So this is a poster, okay, for this company. This company is South of the Borders Inc. So you have custom wallpapers and borders. Okay, free estimate. This is their phone number, so you can call this company to do this. Okay, so what does this company do? This company is a custom wallpaper and borders manufacturer. While their products vary in the visual design, the manufacturing process for each of the product is similar. So when you print wallpapers, you're going to print them in large quantities. Okay? So each day a sample of 100 rows of wallpaper border is sampled. Okay? Each day you are going to collect a sample. This sample includes 100 rows of wallpaper. Then the number of defective rows in the sample is noted. Okay? The number of defective rows in samples from 25 consecutive production days follow. Now we need to determine the control limits for the P chart. So here, this is day 1. I take 100. Day 1, I take 100. Then 13 of them are defective. Day 2, I take 100 rows. 4 of them are defective. And then day 25, I take 100. Then 10 of them are defective. So how many rows in total we sampled? That is 100 multiplied by 25. Okay, it's 2,500. How many of them defectives? You add all of them up. Okay? So total number of items sampled is 2,500. Total number of defective items is 196. How did we get this 196? Anybody? How did we get this 196? Total number of defective. From here, how do we get 196? Any idea? 196 is the total number of defective items. Total number of defective items is actually you add all of them up. This is 196. Then the P bar will be 196 divided by 2,500. Okay, SP will be P bar, 1 minus P bar, and then divided by sample size. Sample size is 100 each day. Then in this way, we will be able to get the center line, upper control limit, lower control limit, 2 standard deviation warning line, and the upper and lower standard deviation. So, but note this is a proportion defective. This one is minus, so this is not applicable because the lower control limit has to be 0. So that's why this is what we have drawn. Okay, center line P bar for defective wallpaper rows. Then you have plus minus 1 standard deviation lines, plus minus 2 standard deviation lines, plus minus 3 standard deviation lines. Then, as we can see, everything is approximately normal, but only you have 2 of them. They are exceeding the volume limit. So you may watch these 2 points, okay, to see what's going on in that day of production. So the observation is no violations or no systematic patterns. This implies that the process in a state of statistic control, and it does not indicate that we are satisfied with the performance of the process. Okay, we can continuously improve the process. It does, however, indicate that the process is stable enough in its performance, and we may seriously engage in the PDCA for the purpose of long-term process improvement. So again, what is PDCA? PDCA is a plan, do, check, and act. Act means once you check, you find some out of controls. Act means you're going to control you're going to eliminate the root cause, improve the process. Okay, so this part, so far we finished the P chart. In the next class, we're going to talk about MP chart and D chart and C chart. C chart and U chart. Okay, I will see you in Thursday.